Mista, for your introduction. And thank you, everybody, for coming here to listen to me. I'm very honored to be in a university like this, surrounded by so many brilliant researchers. So I'm very happy to be here, and I have to thank the department, and especially Professor Vidakovic for the arrangements and for these 14 days that I have spent here. We have been working a lot, and so these days have been very fruitful for me. So I'm very happy to be here today. So this work is part of two research projects that we have in Spain. The first one is funded by the Spanish Research Agency, and the second one is funded by the European Union. So I'm obliged to thank the projects. So these are the projects. And let me please introduce a little bit about the place where I come from. I work at the University of Cádiz. You can see here where Cádiz is located. It's in the very south of Spain, and we are very close to Morocco, indeed. Cádiz is a very nice city. It is a small one, 100,000 people, and it is said to be the oldest cities in Europe. It was founded by Phoenician civilization 1,000 years before Christ. So a lot of history there. There are many, many beautiful places to see. And we are very well known for our beaches. We have amazing beaches, as you can see here. So many of the Spanish people spend their holidays summer holidays in Cádiz or close to Cádiz. And we have, as I said before, a lot of historical buildings. This is the old cathedral, which is very, very nice. So if any of you is interested in coming to Cádiz, just please write an email to me and we can arrange your visit. It's very good for you to come to Spain. There are many places very nice to see. So the work I'm presenting today is joint work. This is Professor Emilio Carrizosa. He's a full professor in operational research in Universidad de Sevilla. Sevilla and Cádiz are very close together. We are both the supervisors of this boy, this guy, a PhD student, Rafael Jimenez, which is very smart and diligent student. And this work is part also, of course, of them. So the research I'm going to talk about today is related to fairness in prediction models. So we will spend a couple of minutes, maybe more, just giving some insight about what is fairness in machine learning or in prediction models. So organizations today usually make data-driven decision models in order to take decisions, to make decisions. And in some contexts, these decisions may have a very significant effect over people's lives. For example, consider the case where a company is studying if should hire a certain person, or the case where a university has to decide if whether admitting or not a certain student, or maybe for example, is a patient expected to need extra medical care in the future, or should a bank label a client as potentially defaulting, or even how likely is a convicted person to reoffend. So situations when making a decision in this context, the answer to these questions has a strong impact of the person who is under evaluation. So what sometimes occurs is that we get biased predictions. There are some real examples very well documented in the literature where you can find this kind of biasing problems. For example, in 2019, an algorithm that was used to predict which patient will need extra medical care favored white patients against black patients. So you can take a look at this paper published in Science where this problem was very well described. So in 2015, the company realized that the algorithm that they used to hire employees for high qualified technical jobs was biased against women. So As another example, in 2016, it was found the COMPAS algorithm, which was used in the United States for criminal justice, produced higher false positive predictions, which means that high risk to commit a crime for Black people than for white people. So there are a lot of controversy about these problems, and these biasing problems occur because when the algorithm is trained, it is trained using some training data sets that may contain some biases regarding some sensitive attributes as gender, ethnic origin, religion, or whatever. So if these biases are present in the training data sets, the algorithms are going to reproduce this bias. So for example, in the first case I showed you before, what happened is that there were more white people than Black people with high health cost in the training data set. In the second example, it was found that there were a proportion of women working in most of technology companies. So this fact made the algorithm to spot and reproduce male dominance. And as an example, it was found that in the training data set, there were a higher proportion of Black reoffended people than white people in the training data set. So this was the reason. The reason was in the training data set, so biases were reproduced. So there have been a lot of reactions regarding this. At least in the European Union, there is a big concern, both from both public and private institutions. And the authorities recommend the use of machine learning algorithms that produce not only explainable, interpretable, and transparent solutions, but also fair solutions. That means that they are not affected by biases in the training data sets. So maybe you can think about a possible way to remove this bias by removing the sensitive variable, the protective attributes you can remove from the training data set. But actually, this doesn't work, because even if you this variable, then there are some variables that remain in the data set, in the training data set, that are highly correlated with the one that you approved. So this doesn't work in practice. So the question is, can algorithms identify some predictions are not affected by this type of biases in the training data sets? And the answer is that yes, they can be modified. And actually, fairness is a very hot topic in the scientific community nowadays. So there are three ways of addressing fairness. We have the in-processing methods, pre-processing methods, in-processing methods, and post-processing methods. The pre-processing methods consider the bias in the training data set are corrected before or prior to the use of the algorithm. So, for example, in this paper, that's what they do. In-processing methods, what they do is to modify the prediction algorithm so that in some way the degree of fairness in predictions is controlled. This is an example recently published in Biometrics. The last way to address fairness in machine learning is the post-processing. The post-processing implements the algorithm, and then once the solution is obtained, the solution is corrected after it is obtained. Okay, so 3 ways. So another critical issues when addressing fairness in machine learning is the choice of the fairness metric, because we talk about we can say that a method is fair, but always fair with respect to a specific fairness metric. So in the literature, there have been proposed many different measurements for measure the unfairness of predictions. And actually, this paper, authors report 100 measures that are defined in terms of performance measures and classifications, the true positive rate, true negative rate, accuracy, or whatever. So it is a fact that there is a difficulty to compare alternative approaches and evaluate their global applicability. This is one of the issues regarding fairness, that when you say that your method is fair, it is fair with respect to a specific fairness metric. So in any case, a metric should result in a tractable mathematical problem, should be easily interpretable, and of course, should make sense in the context we are considering. So in this talk, I want to present another in-processing approach. So we have addressed fairness using an in-processing approach that for a specific selective fairness metric and without using privacy-sensitive information results in fair solutions for the classic linear regression model. Okay, this work is conditionally accepted under minor revision, so hopefully this will be published soon. And so at that time, this talk will be devoted to present this approach. But in the end, I would like to discuss with you the case of fair logistic regression, how to consider fairness for Bayesian for fair logistic regression, which is an ongoing work. And this is going to be considered from a Bayesian perspective. Okay. So I'm going to talk a little bit about linear regression models and Bayesian inference for them, which is very well known. We have our response variable. I'm sorry. So here, the response variable. Here, the design matrix X on beta parameters. So the error is expressed as a Gaussian distribution with this precision parameter. And Bayesian linear regression is very well known from a long time ago. And you can take a look at this book, for example. We've considered here the norma gamma conjugate prior scheme, which imposes says that beta relation to the precision follows this normal distribution, and the precision follows a prior gamma density. So here the hyperparameters are given by this A, B, beta C, which is a vector sigma, which is a simple definite matrix. So the posterior distributions are computed in a straightforward way. They maintain the same structure since the model is conjugate. So here the posterior beta is norm, and posterior phi, the precision is also gamma. It's normal gamma. This is the calculations that you need to compute the parameters. Okay. So the prediction theory is also very well known here. If you are given new individuals with observed design matrix, capital Y, why not? The capital W, yeah. Then the posterior predicted distribution is a multivariate student T distribution with these parameters. So in particular, the posterior predicted mean is given by the design matrix multiplied by the posterior mean of the beta parameters. Okay, so we are going to use this a bit later. So to get fair predictions in this setting, in particular, we wonder how the hyperparameters be selected so that the degree of fairness in our prediction is controlled in some way. But as I said before, the metric for measuring the fairness is a critical issue. So how to define fair predictions? So this is what I'm going to talk about now. Just for notation, we need to define this indicator variable. We will say that for a given individual I, then X equals 0 if this individual belongs to the sensitive class, and if not. So I have to make a remark that S is not the p-predictor variables that are going to be considered in our regression model. So in this way, memberships don't have to reveal the membership to the class, because in some context, this is private, and you don't need to give this information. Okay, so this is important, but we are going to consider this indicator variables as a predictor. So then, if we are given our sample responses, we define the nature of the bias with respect to the sensitive variable S as this difference, which is the difference of average responses between the sensitive and non-sensitive classes. So we compute the average response for individuals belonging to the sensitive, the average response for individuals belonging to the non-sensitive class. We make the difference, we do the difference, and this is kind of measured for the bias on the data with respect to S. If this U is large, we could affirm that we could state that there is bias against this sensitive variable, this protected attribute, in terms of this measure. Okay. So now consider a Bayesian counterpart of this measure U. So since the expected posterior prediction is going to be WY times beta 1, then define Bayesian analogs to this as this difference, okay? Where this guy here is a vector, and the element J in this vector is the average of predictor J among the belonging to the non-sensitive class. The other one is the same for to the sensitive class. So this is like a Bayesian way to measure unfairness. And this is going to be the measure that we are going to consider in this work, throughout this work. It can be shown that here is the expected value for a random, which is this capital U, which is greater in terms of the predictions, posterior predictions. Okay. So the aim is to control the unfairness for posterior predictions. How we are going to do that? We are going to impose this unfairness constraint. This unfairness constraint that states that my unfairness measure in absolute value cannot be larger than fixed threshold that I'm going to give, which is epsilon. Epsilon denotes the maximum degree of unfairness that I'm going to allow in my predictions. Okay. So consider an empirical base setting. So in the empirical base framework, the hyperparameters, which in this case are, I say again, A and B, because real values is a vector and the sigma matrix. So they are chosen to maximize the marginal likelihood. Okay, this is the traditional empirical base framework. You select the hyperparameters so that your marginal likelihood is maximized. In this case, the marginal likelihood is proportional to this one. Okay, this is now. And what we are going to see here is a constraint empirical base approach. So we are going to maximize this term, which is proportional to the marginal likelihood, in a region where the unfairness constraint holds. So I need to maximize this objective function. These are the variables, these are the constraints, and this is the unfairness constraint, okay? So it can be shown that the unfairness constraint holds if and only if the beta 0, which is the hyperparameters for beta, belongs to this region, okay? So this region is stated in terms of the design matrix of the training data set, the design matrix of the individuals that are going to be predicted, responses, and this hyperparameter. So this is written like this. And I wanted to notice how this C is the difference between the average, the predictors between the sensitive and non-sensitive groups. So this is the fairness constraint is written in terms of a region. So now we need to solve this constraint maximization problem. We have one complex objective function. Because of the complexity of the objective, this last constraint to some kind of multi-stack strategy in order to be stuck in a poor local optimum. Okay, so when some multi-stack strategy is going to be implemented, the choice of the starting values is critical in order to reduce the running times. So I will talk a little bit about this thing later, okay? How to choose the starting points for implementing the optimization of this problem. So I'm going to go to numerical results. First, I will consider some synthetic simulation experiment. We have, just for this is a toy example, we only consider 5 predictor variables, which are a bit unrealistic, but it helps to understand how the method performs. A total of 3,000 instances. Simulate the parameters of the model according to this structure of simulation. And we need to bias the data in some kind of artificial way. So we consider that those individuals with response below 0 are going to belong to the sensitive class. Okay. To bias the data. But this quantity here, which is the expected value of the prior expected value of phi, controls the degree of separation between the classes. This is why, because the variance of the responses is going to be inversely proportional to this quantity. So I can show you here. The bigger this quantity is, the less variability in the response, and so the classes are more close to each other. Okay. So here we have more separation between the classes. Here we have a small separation between the classes. So the problem for a grid of values of epsilon chosen according to this grid, the variable scale. Apply the MATLAB routine global search, which is for global optimization. And we don't impose any time limit. So this is important because if you say 200 seconds with time limit, you have no guarantee that you get the optimal solution. Okay, so without any time imposed, you get a best solution. So as I said before, the choice of the starting point for a guided search is relevant, it's crucial in this context because it reduces a lot of the running times. So what happens here is that the search regions in our optimization problem are nested. So if epsilon I minus 1 is less than epsilon I, then the regions are going to be included. So what we do is for epsilon I, when running the problem for epsilon I took the starting solution, the optimal solution of the previous solved optimization problem. So in this way, we don't start in a bad random starting point. It's just a guided search. And this reduces a lot the running times. One cannot expect to attain fairness for free. So we have going to pay a price in order to calibrate how the predictions are distorted because of the fairness measure. We need to set up a kind of accuracy measure of predictive error. So for that Mitchell and Beauchamp used in this paper published in JASA. So they define this random variable D as typically defined. So this I is the difference between the observation of the predictive density. So this is random variable. What we are to use to model the predictive power of my approach is the expectation of this random variable t. Okay, this is going to be our predictive error. To estimate the predictive error, we're going to use a 5-fold cross-validation approach. So we define the error according to this expression. So in the full number k, so we divide our sample. Okay, in the full number k, we are going to train the model with the training data set, and we are going to compute the error as a difference between the real test sample minus how we predict this test sample according to the parameters estimated from the training data set. This is the way we should do the predictive error for cross-validation. So here you can see the left picture. You can see the trade-off between the value of epsilon, which was the maximum degree of unfairness that I am going to allow in my predictions, estimated predictive error. So we have two columns. The red one represents the results when for the training data set. The correct thing would be to show only the test results. But for the sake of comparison, I've also shown the results when the validation test equals the training data set, which is not what it has to be done in practice. In practice, what we should take a look at is the blue columns. But for comparison, I hope I also obtained the results where the training data sample is used as a validation. So you use the same data set for training and for validation. We all know that shouldn't be done for comparison reasons. So these are the columns regarding the columns. Regarding the cubes, the solid lines represent the estimated expected value of the estimated predictive errors. On the dashed lines, some prediction intervals. Okay, so you can appreciate on the straight lines represent the predictive error when unfairness measure, unfairness constraint is imposed. So it's for the unconstrained problem. So you can see here how when I from left to right, the error decreases. So I'm getting better accuracy. I'm getting better model for in terms of predictive power. But if I move to the right, my solutions are less and less fair. If I want a very fair solution, I have to move to the left, and in this part, the error, as it was expected, increase. Okay, so you can also notice that we obtain more variability for the test sample than for the training sample results, which was also expected. And again, well, this is more or less the message. When we are going more and more less and less fair, the error decreases, so we do better in prediction, but we do worse in fairness. This is the trade-off. So even if it's an unexpected outcome, so we expect to obtain a decreasing pattern here, there is no guarantee that this occurs for all data sets. And this is because what we are optimizing is not the predictive error, but this function f, which was proportional to the marginal likelihood. So this is the function that has to have a monotonic pattern. And indeed, it increases with the value of epsilon because of this thing about the nested regions. So if I move to solutions that are less and less fair, my objective function is going to increase. And this is always going to happen. Okay? This decreasing pattern is expected, but there is no guarantee for this. And this straight line represents the solution, the objective function evaluated in the solution of the unconstrained problem. Okay. So The Bayesian perspective allows for a better modeling of the uncertainty. And here, what I depict in this picture is the histograms for the random variable D, which was this one. This is the predictive error, which is the expectation of this random variable. So we are going to simulate we are able to simulate from this D, and this is what I depict here, the histograms for, I guess it was 1,000 simulations of D. And let's take for the first form of the cross-validation approach. Red represents the results using the training sample, blue the test samples, and then the darkness, the darkness of the colors is associated to the degree of fairness. So what we observe here is quite similar to what we observed in the previous picture. For test sample, we get more variability. The train results are less variable. And we are very demanding regarding the fairness of my solution. That is when epsilon goes to 0, which is the lightest cases, the red light and blue light, then the values of the random variable shift to the right, which is expected. We get error in the predictions when we are very demanding with our fairness constraint. So now I'm showing you here how the unfairness metric evolves of the values epsilon. So here it shows the evolution of this quantity for the train or for the test samples. And the dotted line represents the value of epsilon in logarithmic scale. So if we make a zoom at this picture, we see that the red line is always behind the dashed black line. And this has to be like this because this is what I'm using, my optimization problem. For this case, I impose to have fairness in the prediction of my training data set. But I didn't control the prediction of the test sample. So that is why the test sample is a little bit above the value of epsilon, because I don't have control over there. But the program allows for changing these two samples. So even though I can't train with the algorithm with the training data sample, I can impose my fairness constraint over the test sample, because the only thing I need to be clear about this, when we consider here the unfairness constraint region, which is written like this C is what I need regarding the design matrix of the individuals to be predicted. So I want this C if the individuals are those of the test sample. This would be the degree. Now, fairness control would be over the test individual, the individuals from the test sample. But if WI, it's computed, this C is computed using the trained sample, then the unfairness constraint will be imposed over the trained sample individuals. So the method is flexible enough so you can establish where you want to impose the unfairness constraint. Okay, I was here. So that's what I was telling you. Since here I use the individuals of the training sample to compute this C value, the red line is always below the black line. If we simulate, because this is a simulational example, so we have all samples equally distributed, so we don't expect to have much difference between the training and the test, but for a real data set, it can make a difference, okay? So similarly as the previous slides where I show the picture of the histograms, the density, approximated density for the random variable D, we can do that also for the random variable U, which was related to the unfairness measure. My unfairness measure was the expected value of this random variable U. Okay, so we have different degrees of fairness. Here we are very demanding. Here we are less demanding regarding the level of unfairness. And of course, when we are less demanding, this unfairness, you can see here the range of values increase. These are very low range of values. This is times 10 to the power of -3. So if we want a very, very fair solution, these histograms are going to move to the left. Okay, some referee asked about the comparison with benchmark methods. And this question is not trivial at all because we have a linear regression, Bayesian setting, a specific fairness metric. So how can we obtain methods for comparison in a fair way, our approach, for comparing in a fair way our approach? So what we did was to create the frequentist approach of our method, which is a constrained maximum likelihood approach. So we maximize the likelihood function. In this region, this would be the unfairness metric in this frequentist setting. So these are two randomly chosen instances. You can see here the box plot of the posterior predictive distributions for each instance. Let me see, the blue point is the true value, and the black point is the maximum likelihood prediction. So these are some for two different levels of unfairness. Again, we are always comparing a very demanding solution with a less demanding solution in terms of unfairness. We wonder how the level of unfairness affects to the estimation of parameters. So what I plotted here, what I depicted here is the parameters of my model, with only 5 predictors, the true value of the simulations, and these are the posterior expected means for this beta and these phi's, and the maximum likelihood estimates for 2 different degrees of unfairness. So here we are very, very fair. We want to be very, very fair. Here we don't care so much about the fairness. So in this case, the unfairness constraint doesn't play a real role. See now, it's what approaches perform similarly, a lot of instances, so it's expected. But here we have much more distortion regarding the point estimates for the parameters of the model. So in some cases, we estimate pretty bad. Here we go to the positive line, and this parameter is negative. So of course, this is related to the price to pay when you are imposing fairness. You are losing predictive power, and the goodness of your model is smaller. So we also thought that it would be good to compare with other kind of prior structures. So what we did, the thing that if we use the conjugate normal gamma model is that it has a lot of parameters. So if P is large, we have this amount of parameters, and this is bad for computational time, for computational reasons. So we decided to do two things. Assume that this covariance matrix is diagonal, so we reduce pretty much the number of hyperparameters, and to use this standard G prior, which is a simplification of the normal gamma, because it just considers that the covariance matrix depends on this J parameter. So here we go from this huge number of parameters when P is very, very large to P plus 4. So we compare not both, the 3 prior structures. And when we got, we have 3 measures for comparison. We have the objective function, which was proportional to the marginal likelihood, the estimated predictive error, the Davis information criteria, the TIC value, And got that regarding estimation, the three models behave pretty similar. They are more or less behave. So if we fix the epsilon, these values are more or less very similar. The difference appears, of course, when we go from one epsilon to another one. So, and this in terms of fitting the model, both prior structures behave pretty similar. So the impact is so models, the different models have a real impact on the running times. So increase P from 5 to 100, what we get is the running times for the complete model. The running times increase by a factor of 200. It's from 5 to 100. So the simplified parameterized models, we obtain comparable times, and both times were increased by a factor of 40. So it's not so bad as with the normal gamma conjugate normal, the full version. But if it's 2p plus 1000, the time increases dramatically. So in this setting where p increases so much, we discard for sure the full normal gamma conjugate model, because we saw in this experiment and in others that we don't have a real gain in terms of accuracy, and we pay a very high price in terms of running times. So we consider that when we go for a P which is high, we are going to use the Cernus prior structure. If you to use the complete prior structure, you need to impose some time limit unless you want to be waiting infinite time. So you can impose some time limit, but this is there is a consequent uncertainty about the character of the solution, maybe a local optimum. So the solution would be worse. But we suggest in the paper, we suggest to use the Cernus pre-prior, which gets a balance, a well balance between running times and prediction. Okay, so these are the results for I studied at 11:30, right? 11:30 was the time. Okay. So the results for an large data set. I'm not going to comment again about this, but I just want to make a remark, is that, as I told you before, this has to be always increasing. We observe here, but look at this, Pearson peak increases a little bit. So, as I told you before, we have not guaranteed that this is always increasing. It should be expected that output. Sometimes we don't. Okay. So I'm going to illustrate the method over a real data set, which is in an educational context. This is a very well-known data set, student performance. It is composed of 633 instances, which are students. We have 25 predictors, and the response is the final grade for the subject of Portuguese. So the sensitive variable here indicates whether a student has internet at home or not. If you take a look at the distribution of the responses, you can see the yellow samples are those of students without internet at home, accessing internet at home, and the students that have internet. So you can see here that these are the sample means. So for those students which don't have internet at home, the average response value is smaller. So we would like to correct this bias in our prediction model. So now I'm not going to do cross-validation, not dividing between train and I'm not going to do cross-validation. I just consider that the 80% of the total is like a historical sample of students. The 20%, the rest 20% to be the forthcoming students that are going to be predicted in a fair way. So for those individuals that I want to predict, these forthcoming students, we assume the design matrix, okay, that doesn't contain individual information regarding the variable S. So we know this design matrix and the value of C. So if we don't know the S, but we need to know the value of C, which is the difference between the both classes. So we make the fairness constraint to be satisfied all the predictions for the prediction of these 4 common students. So here we get some results, quick results. This is the objective, the expected, estimated and expected of the unfairness measure. So this is the same message when I want to have a very fair solution. Everything regarding the prediction worsens. Okay, you can see that the value of the unfairness metric is always behind the epsilon. Okay. So you can see here, these are posterior predictive distribution for students. You can see this case is the case where epsilon is 0.01. So we want a very fair prediction. So cut the averages, they are almost the same. Here we are not so demanding concerning the unfairness, so the averages are a little bit separated. So I've introduced an approach that considers fairness constraint in prediction for the linear regression, classical linear regression model in a Bayesian way. Constraint empirical-based estimators by maximizing the marginal likelihood in a constraint research space. And it's important to show the trade-off between the level of unfairness and the accuracy. So this is important for decision makers. If I need to make a decision and I want a fair solution without losing very much in prediction, I have my picture, I can take a look at the values of epsilon, so I take the one that interests the decision maker. And so in some sense, this problem was not very, very difficult because we have closed form for the posterior distributions and closed form for the posterior predictive distributions. But what happens if we don't have these properties? For example, when we are going to address linear logistic regression. So in logistic regression, it is not possible to find the posterior in closed form, not the predictive posterior. So some kind of approximation has to be considered. There are many in the literature: quadratic Laplace, MCMC, HMC, or variational inference. So variational inference, you know well, is kind of is an optimization-based approach. So we have two variational inference. The real posterior is going to be approximated by some Q star, which is the solution of this minimization problem, which is the solution of the Leibler divergence between the real and the approximate posterior. And this Q gives some family of distributions that they are hopefully tractable. For example, the multivariate Gaussian, something like that. So there are a lot of literature for binary variational inference in binary regression. This paper by Jack and Jonah, this very good book of Bishop, but there are many others. So this is what variational inference performs in logistic regression. We consider this prior structure, which was very similar to the previous work. So we assume the mean field assumption, after the mean field assumption, which states this. Then this approximate Q is the product of these two, and these ones are the first one and the second gamma. And these parameters are obtained in what is called the Gabi equations, which is a set of recurrence equations, coordinate accent variational inference equations. And this is very fast, and this works pretty well. So These are some intermediate steps I'm going to skip. So how to induce fairness in this setting, this is an ongoing work, this is very, very preliminary results. What we propose is, instead of considering this minimization, we consider this one. So the urban library divergence, but we add here a penalization term, this lambda, where this is the unfairness measure, which is dependent on Q, and this is the penalization term. So if we assume that our unfairness measure is the expected value of this some H depending on beta, then instead of this, which is what is obtained in the unconstrained case, we get this one. So here there is a negative, it's in here. So the major problem here was how to select a metric so that this H is quadratic in beta, and this way Gaussianity is recovered. So we found out that we define the unfairness measure as this, we is quadratic in beta, so we recover normality in the approximate posterior distributions. So this is the difference between the loss of the odds ratio for the sensitive and non-sensitive classes. Here, this is random variable, beta is random variable. So this guy plays the same role as the capital W of the previous work. So take a look at this. This is the same thing that we had in the previous scenario. This is like a quadratic version of our previously considered unfairness measure for the previous work of linear regression. So there's some kind of link between these two approaches that we need to investigate in much depth. And what is as we recover normality, and the Gabi equations are exactly the same as we have in the unconstrained problem. But the other thing that changes is when updating the values of this covariance matrix, we have here this term. So this is the only thing, that we get. This unfairness metric is very easy to be evaluated, because this interval is analytic. So we have a closed form expression for evaluating this measure. So if can I finish with 2 lines? Okay, thank you. I'm going to show some preliminary results using the German credit data set, which is a real data set in machine learning used for risk assessment prediction. So the aim is to determine whether it's risky to grant credit to a certain individual. We have 23 predictors, 1,000 instances, and the sensitive variable, we don't say this is an example considered from the literature of fairness. Sensitive variable can be age or sex, opted for age. So it's S is equal 0 if the individual is young. That means that it's less than 25 years old. As a fairness, as an accuracy measure, we consider the expected value of this thing from the variable, the success rate. So we consider the expected value because this is a random variable. And again, we apply a 5-fold post-validation approach. So got 2 important messages. The first one is this. The hyperparameters in this case has a very significant effect over the solutions. So you can see here, I plotted here the success rate for a grid of different hyperparameters. So you can see that the choice of these guys are really, really important, because you can improve very much your success rate if you are choosing smart solutions. So you need to fix the prior hyperparameters to initiate the Gabi equations. So how to choose them, it is quite important. And the second message is very, very similar to the one that we get before, that we pay a price in terms of accuracy. We come here, if I go to the right, what I'm asking is a very fair solution. It was the other way around, the epsilon. So now if a lambda is big and very demanding fairness, you can see here tends to decrease. They are predictive, the estimated error and the predictive, the credible prediction intervals. So on this, I'm done. I exceeded a little bit my time. Sorry for this. So thank you so much for your attention.